In this video, we will learn how to integrate by completing the square in quadratic trinomials. Before we jump into the main techniques, let's take a look at some important integrals that we are going to use. The first one is the integral of 1 over k squared plus t squared dt. Using any table of integrals, we can say that this integral reduces to 1 over k arctan t over k plus c. The second one is integral of 1 over k squared minus t squared dt. Again, using an integral table, we can see that this one is 1 over 2k ln k plus t over k minus t. The third one is the integral of 1 over square root k squared minus t squared, and this one becomes arcsine of t over k. Finally, we have the integral of dt over square root of t squared plus or minus k squared, and this one becomes ln of t plus square root of t squared plus or minus k squared plus c. The plus or minus simply means that when there's a plus in the integrand, there will be a plus in the answer. And when there's a minus in the integrand, there will be a minus in the answer. Also, one thing to keep in mind that the variable of integration here is t, but we could easily replace this with x. For example, the integral of dx over k squared plus x squared would be 1 over k arctan x over k plus c. We are now ready to take a look at the 4 main types of integrals we are going to see in this video. The first type just has dx in the numerator, or a 1 in the numerator if you will, and only a quadratic trinomial in the denominator. After we complete the square for this quadratic trinomial, what we are going to get is an integral of the form dt over k squared plus or minus t squared. Here k is some constant. Now we just saw a few seconds ago how to integrate this sort of function. If it's k squared plus t squared in the denominator, then you're going to get an arctan integral. And if it's k squared minus t squared in the denominator, you're going to get a ln type integral. This is just the same as what we saw earlier, namely the first two types over here. The next type is very similar to the type 1 integral. We are still going to complete the square in the denominator, and we are going to somehow manipulate the numerator to convert it to a type 1 integral plus an integration by substitution. So type 2 is very easily reducible to type 1. Next, let's take a look at the type 3 integral. In the type 3 integral, we have a square root of quadratic trinomial in the denominator. And again, we are going to complete the square for this quadratic trinomial. And this is going to result in two different types of integrals. It could be integral dt over square root k squared minus t squared, or integral dt over square root t squared plus or minus k squared. Now these two integrals, we saw the form earlier. The dt over square root k squared minus t squared can be reduced to an arcsine, whereas the bottom one can be reduced to a ln integral. Again, these are the same ones that we saw earlier, namely the bottom two integrals. Finally, we have the type 4 integral. In this one, we have mx over n, a linear function, over square root of a quadratic function. And again, just how we did for type 2, how type 2 was reduced to a type 1 plus integration by substitution, you can probably guess that we are going to reduce the type 4 integral to a type 3 integral plus integration by substitution. So type 2 and type 4 really can just be reduced to type 1 and type 3. So all you need to know is how to integrate a type 1 and a type 3 integral. And that was all the theory. But how does this work in practice? Let's take a look. The first example is clearly a type 1 integral. Let's first and foremost make our life a bit easier by factoring out a 2 in the denominator. So this integral becomes dx over x squared plus 4x plus 10. Now from basic algebra, you know how to complete the square of this quadratic, and so we have 1/2 integral dx over x squared plus 4x plus 4 plus 6, and this one reduces to 1/2 integral dx over x plus 2 squared plus 6. We can now see that this integral is of the form integral dt over k squared plus t squared. If you really need to convince yourself, you can make the substitution t equals x plus 2. Let's do that actually. T equals x plus 2, and so you have dt equals dx. And this integral now becomes 1 over 2 integral of dt over, I'll rewrite this slightly as root 6 squared plus t squared. I think you should now be able to see that root 6 is the k over here, and the sign in the middle is a plus sign. And as we know, this sort of integral reduces to an arctan integral. Let's recall the result. Integral dt over k squared plus t squared is 1 over k arctan t over k plus c. And so this integral is going to become 1/2 multiplied by 1 over root 6, which is 1 over k arctan t over root 6 plus c. But remember that t was nothing but x plus 2. Our final answer is going to be 1 over 2 root 6 arctan x plus 2 over root 6 plus c. Moving on to example 2, you can probably see that this is also a type 1 integral. Again, we can make our lives easier by factoring out a half outside, and we have dx over x squared plus 4x minus 2. You can verify for yourself that after completing the square, we can reduce this integral to 1 over 2 integral of 1 over x plus 2 squared minus 6 dx, of course. Again, you can see that we want to convert this integral to the form integral dt over k squared plus or minus t squared. Now, since there's a minus sign over here, you can probably guess that we are going to make it a k squared minus t squared integral. To be sure, we can see that the integral of dt over k squared minus t squared is 1 over 2k ln k plus t over k minus t. But hang on a minute. The integral we have here, if we replace x plus 2 by t, is going to be t squared minus k squared. But we want k squared minus t squared. And so we are going to flip the order by just pulling out a negative sign. So this is going to be negative half integral of dx over, I'll rewrite 6 as root 6 squared minus x plus 2 squared. Now that we have the required form, k squared minus t squared, where k is root 6 and t is x plus 2, we are ready to evaluate this integral, and this becomes negative half, and the integral becomes 1 over 2k, which is 1 over 2 root 6 ln absolute value k plus t, so this becomes root 6 plus x plus 2 all over k minus t, which is root 6 minus x plus 2. And cleaning this up a bit, we can just write this as negative 1 over 4 root 6 ln absolute value root 6 plus 2 plus x over root 6 minus 2 minus x plus c. In the next example, we will study a type 2 integral where you have a linear function on top and a quadratic function on the bottom. Remember that type 2 integrals can be reduced to a type 1 integral plus an integration by substitution. To proceed here, we first have to rewrite x plus 3 as a term which contains the derivative of this quadratic trinomial plus some constant term. Let's see what I mean by this. What is the derivative of x squared plus 4x plus 10? That is simply 2x plus 4. So we want to write x plus 3 as a term containing 2x plus 4. How do I do that? Well, x, the coefficient here is just 1, but the coefficient of 2x plus 4 is 2. So I'm going to write this as half of 2x plus 4. But half of 2x plus 4 is just x plus 2. And we want one more to make it x plus 3, so we have plus 1. Now this transformation might seem a little bit tricky, but I promise you, you will get used to it after some practice. Anyway, the point of doing all this is to rewrite x plus 3 as half of 2x plus 4 plus 1, and we have the integral of this thing over x squared plus 4x plus 10 dx. Now using the rules of integration, we can split this up into two different integrals. The first integral becomes the integral of 1 over x squared plus 4x plus 10 dx, and the other integral becomes plus half times the integral of 2x plus 4 over x squared plus 4x plus 10 dx. Now if you remember, the first integral here is just a type 1 integral. And the second integral over here, you can see the numerator is the derivative of the denominator, and therefore this can be evaluated by substitution. In fact, the first integral is very similar to an integral we have already done in this video, that is this one. And as we remember, the integral here was 1 over, well, there's no 2 here, but 1 over root 6, because there was a coefficient of half outside. This is 1 over root 6 arctan x plus 2 over root 6 plus c. I'm ignoring the 2 over here because there was already a half outside. And so we can evaluate this integral as 1 over root 6 arctan x plus 2 over root 6. The second integral can be evaluated by substitution. We can simply set u to be x squared plus 4x plus 10, and therefore we get du as 2x plus 4 dx. And now you can see the point of splitting up x plus 3 in terms of 2x plus 4. That was the whole point of doing this step, so that we can evaluate this integral by substitution. We have already covered substitution in a previous video in this playlist, so I'm not going to explain in too much detail how to perform this integration. So we have half integral du over u. This is just a ln 1 over 2 ln of u, but u was nothing but x squared plus 4x plus 10. Well, the main thing in this one was to reduce the type 2 integral to a type 1 integral. Basically, we broke down a complicated problem into two simpler problems that we already know. Namely, we broke down a type 2 integral into a type 1 integral and an integration by substitution. In the next example, let's take a look at the type 3 integral. Now for this one, again, we have the familiar x squared plus 4x plus 10, and we already know how to complete the square. So this is going to become the integral of dx over the square root of x plus 2 squared plus 6. If you remember in the type 3 integrals, after completing the square, the integral reduces to one of these two forms. And considering there's a plus sign in between these two terms here, we can see that it's going to be the second one. So, referring to our table of integrals here, we can see that t here is x plus 2 and k is the square root of 6. And so this integral simply reduces to ln absolute value of x plus 2 plus the square root of x plus 2 squared plus 6 plus c. Very straightforward, yes? Now that you're familiar with the type 1 and type 2 integrals, you can see how similar the type 3 integral is to the previous ones. We're just using a different result from the table of integrals, but the techniques are the same. Moving on to example 5, this one might look a bit awkward because of this negative sign outside the x squared. But that's not really an issue because we can still complete the square even if there's a negative here. The way we do that is to pull out the negative sign, and we have negative of x squared plus 4x plus 2, and completing the square inside the bracket we have negative of x squared plus 4x plus 4, and since we've added a negative 4 inside, we have to add a positive 4 outside, so it becomes plus 2 plus 4, which then becomes negative of x plus 2 squared plus 6, and we can rewrite this as 6 minus x plus 2 squared. And so our integral is going to be rewritten as the integral dx over the square root of 6 minus x plus 2 squared. Now you can see that this one looks like the top integral, that is dt over square root of k squared minus t squared, where k is the square root of 6. And as per our table of integrals, integral of dt over square root of k squared minus t squared is simply the arcsine t over k. So this is going to be arcsine of x plus 2 over square root of 6 plus c. For the last example, let's take a look at a type 4 integral. Now do you remember that for a type 2 integral, we converted it to a type 1 integral plus an integration by substitution? We are going to follow the same approach over here. We are going to convert a type 4 integral into a type 3 integral plus integration by substitution. And turns out that the numerator and the quadratic are the same as the type 2 example. So just to remind you, we rewrote x plus 3 as half of 2x plus 4 plus 1. And so we can rewrite this integral as the integral of 1/2 2x plus 4 plus 1 all over the square root of x squared plus 4x plus 10 dx. And again, we can split this up into two different integrals. The first integral is 1 over square root of x squared plus 4x plus 10 dx, and the second integral is plus 1 over 2 integral of 2x plus 4 over square root of x squared plus 4x plus 10 dx. The first integral we have done before in example number 4. Let's go back and check. Example 4 is the exact same integral as the first term in example 6. And so we can just write the answer as
ln x plus 2 plus square root of
and the second integral, as you remember, we can evaluate this by substitution. We can set u to be x squared plus 4x plus 10, and therefore du is 2x plus 4 dx. And therefore, this integral reduces to plus 1/2 integral of du over the square root of u. This is an elementary integral, and you know that this reduces to square root of u. And so we can write the final answer as ln x plus 2 plus square root of x squared plus 4x plus 10 plus the square root of x squared plus 4x plus 10 plus c. As usual, here are some practice examples, so you can pause the video and try these out on your own. Answers will be revealed in a few seconds.